Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Hi everyone, thank you for coming for this last day of the series of lectures by Jeffrey Fox. We've been having a lot of fun, I think, and we know that there are a lot of people watching us live. I just wanted to close this, to start this final day by thanking Jeffrey a lot for his time and effort in this. He has made this a lot of fun by allowing it to be interactive. He has obviously put a lot of work behind it, a lot of preparation. He has been part of the entire history of parallel computing by contributing so much, and we are really honored to have him here. And I would like to thank him for accepting our invitation to come here. I'm not gonna bore you with things about Jeffrey. We all know him. He's a leader in this field. He's a leader now in grid computing, and in looking into the future of grid and the web 2.0 and all the fun stuff that we do in high performance computing, parallel computing, grid computing. I would like to just give the floor to Jeffrey for this final day. I'm really looking forward to it, and again, thank you very much, Jeffrey.
Thank you, and certainly it's been an honor to give these talks, and thank you for inviting me. And I also hope to be part of the future as well as the past. So I thought I'd start off today, this is the last lecture, just reviewing some sort of overall useful information for people wanting to follow through. Here is a useful website, www.conatia.org/user/CRMC. Conatia is nature's internet annotation service. If you like, it's the nature's version of Delicious, if you know Delicious. And I have collected on this site 177 references in the area of parallel computing and multicore. And you can, on the left-hand side of this screen, you will find all the various tags here. So here I've tagged all these links, these 177 links. And if you press a tag, you will find the links which satisfy that tag. And if you press applications, you will find these are the links, for instance, that have the word applications, of which there are just 10. So you can play with that site. The top link here, Conatia, for some reason, always lists the link you add last at the top, which isn't obviously a good idea because it's possibly recently in this collection here is probably often the least interesting because it's the ones I added at the last moment. But the top link at the moment is this particular lecture sequence, and if you press that, you will go to this very elegant web page here, which just is a list of all my presentations in PowerPoint form, and you are welcome to download them and do whatever you want. And I gave a short description of what they are. And there are many, I did not use some of the presentations I prepared, but they're all placed here if you wish to use them. There's a whole set on scientific applications that we will not have time to go through. But you don't actually have to remember this rather longer URL, because you can find it from conatia/user/CRMC. CRMC stands for the Center for Research in Multicore Computing. So that's the end of that discussion of where you find out more further, you follow up later. Now we go to the, well, I think what I'll do is I'm going to go to, so we had a question about load balancing. So I will do load balancing because it's at the end. I will do a peculiar discussion of load balancing. Okay, well, why don't we just start? Oh, here's Tony. All right, so as Tony is here.
You've done your homework, have you, that they set you?
Oh, yeah, I do my homework, yes. Well, actually, let me summarize the homework while Tony's here, because at least this might be helpful to him. I wanted to just do this. So as a summary of what we did, as well as this discussion of the overview of parallel computing, my homework was to go through the Intel application stack. I was requested to go through that. And so what I did, so this is the slide from Intel, and I put a little red tick on those applications that are covered in the slide set. And so that is support vector machine training, integer programming, frequent item set mining, and k-means are the applications that were discussed in detail in that slide set over the last 2 lectures. If you look at the other applications, I honestly don't know what particle filtering is, but I believe the other applications are all clearly parallel because they're just standard scientific applications. So the homework was to focus on the applications which weren't covered by scientific computing. So the claim would be that the combination of this slide set and the folklore on the expertise on scientific computing suggests that you can take this Intel stack, which they claim is going to be important for multi-core chips of the future, and you can produce good parallel implementations for these. So that information is available in those slide sets.
I would say they claim that this will keep their processors happy.
That's right, yes. Whether they keep the users happy is not so clear, but anyway, but at least this is as far as I know, this particular study by Intel is, at least in my opinion, quite important because it's one of the...
Intel identify those algorithms as the major ones that are suitable for their...
That's right. So at least Intel, when Justin Ratner presented this, so it must be endorsed at some relatively high level. They thought about applications and they came up with a suite, and this were the kernels which would drive that suite.
Just to give some perspective on that, they did come and talk to us actually when developing the suite, so there is a bit of self-referential stuff going on, just to warn you about that.
No, that's fine, that's fine. No, it seems a plausible set. Yeah,
it's a reasonable set.
But this way you also get the community excited about it. I mean, you give direction. I mean, everybody's now working on it. Come on.
It's a good idea. But have they targeted this specific architecture with their memory access?
No, I don't think they. No, this was Intel has an application group. This application group, as I understood it, was looking at what might run on multi-core clients of the future.
But how well it will run will depend on the memory hierarchy and stuff like that.
Yes, so that's up.
This is the roadmap, so it's now to us to make it happen.
Indeed.
Yes, so that's what I said. I would claim that so I actually like this slide because I did think that everything would run pretty well. I didn't do the detail until I did the homework. And so this is an encouraging slide. It says that there are a rich set of interesting client-side applications which will run well on multi-core chips and make use of many, many cores. And these effectively all of them have scalable parallelism, as far as I can see. So that I think is, whether this is, so it's actually pretty interesting to decide whether this is a good study. And if it is a good study, there's sort of a non-trivial activity called develop some of these applications. So that's All right, that's the end of that slide. So that's just a summary of the last what we did. So now we go back to the
Actually, you're using Office 2007.
yes. Although I prepared it on Office 2003, but it's as being... all right, so a special request. I'm going to first go through some slides about about load balancing. And I'm not certain I want to do this slide. Okay, well, we could. All right, so these are very old slides, and these are rather simple slides. And we've already mentioned that particle dynamics has rather complicated load balancing because you get lots of clustering, which is quite extreme if you start doing cosmological simulation. If you do the simplest equal area decompositions, you lead to load imbalance unless you happen to be doing the world's simplest algorithm, which is the order n squared algorithm, when actually the geometrical structure doesn't matter, because if it's order n squared, every particle talks to every other particle. So you just need to put equal numbers of particles in each processor. It doesn't matter about geometrical locality. If these forces are local, you need to choose a decomposition that has actually got geometrical structure. So that's sort of so here we have an example of a geometrical problem with all right, so here we have four. We have there's a difference between a scattered and a block decomposition. So this comes back to your question about robust decompositions versus optimal decompositions. If you wish to reduce communication, you want to assign to each processor a domain which has the smallest edge over area, which for a simple, so here we have four processors, red, white, purple, and black. And the top decomposition is the sort of optimal large geometrical domain, and they will have the smallest edge over area because that's a large area, and the edge over area goes like 1 over the square root of the perimeter.
These algorithms just have nearest neighbor.
We're talking about the geometrical decompositions are only needed for effectively nearest neighbor type algorithms. If you have a long range algorithm, you don't have to do geometrical decompositions.
Well, actually, what you're saying in my world is use the logical structure and make it on the physical, meaning on the processor side, visible.
That's right. Yes. I mean, I pointed out that you can always think of parallel computing as a map of the application onto the processor. In order to get good performance, you need to make that map make the application structure map properly into the processor structure. Now, there is this so-called scattered type decomposition, which takes each processor and scatters it around the domain. And that's shown here. So we take the white processor and put it in those 4 areas, and we take the red processor and put it in those 4 areas. And that decomposition is actually more robust because as points move around, like if you had a black hole forming in the top somewhere here, then that white processor will get all the work in the top decomposition. If you take this thing here, it will get shared. So this is an example of a worse decomposition because it has more edge over area. However, it is more robust. And you always have this trade-off between optimal and robust decompositions. So here's this black hole or something, or an earthquake occurring at the top. That earthquake occurring at the top is a catastrophe. I mean, this is again this dynamic idea. Supposing you had something happen which required a lot of extra computing, and if happened inside one processor, you're doomed. And so this star here is meant to represent an earthquake or a nuclear bomb falling or something in your simulation, or a black hole forming which causes extra work. If these optimal initial decompositions cannot cope with that, whereas appropriate scattered decompositions can.
But they have a larger communication.
But they have larger communication. So this is natural. Robust is not as good in any one case, but it is much more stable on perturbations. This is really old. So here is the class. So this is the, as I mentioned, these mappings of irregular problems onto processors is a well-known NP-complete problem, and I pointed out when I gave my talk in '84 at UCLA, they said, well, I didn't even know what NP-complete meant. They said, well, this will be a disaster, and I put it into my next DOE proposal, and it turned out it wasn't a disaster, but it was fine. So here we have a finite element code, and here's the various mesh on the left there. If we did an equal area decomposition, it would be a catastrophe, and one of the processes, the one here with all that, that's where a crack is developing in the plate, would have most of the work. So that's no good, and it is possible to find all sorts of optimal decompositions, and here's one we found here, which it gives a much better workload. Here's the actual workload here. Notice an important point, which is why NP completeness is not so obviously relevant. It is not necessary to get optimal load balance. 10% is fine given all the trade-off one has in life. And the theory of optimization, this is an optimization problem. So the optimization, the time complexity of an optimization needed to get 10%, something good to 10% is not nearly as bad as the optimization needed to get the best answer.
So it's the same as the traveling salesman.
Yeah, this is formally the traveling salesman. If you only want approximate traveling salesman, there are many, many heuristics.
In query optimization in databases, we say you don't want to have the optimal plan, but you want to avoid the worst plan. This also applies here.
So that is but it's an important observation because it explains why this is not as hard a problem as you might have thought. It is because we are getting reasonable, we want reasonable decompositions. We do not want the best.
The 80-20 rule holds. I mean, you want to do things with reasonable amount, and you don't want to squeeze out the last X%, which costs you a humongous amount of work.
So that's that. We'll skip that one. So let's just finish on this physics analogy. Burton reminded me of this physics analogy. And this explains these this is one particular way of doing this, which, if you like, corresponds to using the simulated annealing is a well-known optimization algorithm, which can be thought of as mapping the optimization problem into a physics problem. In the case of this particular load balancing case, the physics problem can be thought of as imagine a world full of processes or threads, and we wish to assign, and we have, say, more threads than we have processes. We wish to assign these threads could actually be individual grid points, and we wish to assign those threads to processors for load balancing. And the way the physics analogy is to map every thread into a particle. And then we wish to write down an energy for this system such that minimizing the energy corresponds to solving the load balancing problem. And an appropriate way to do that is shown here. You can write down a Hamiltonian, which isn't the exact execution time, but it has two terms in it which correspond to the two aspects of load balancing. One is equalizing the load on each CPU, and that is done by least squares minimization of the sum of the squares of the total execution time on each node. The other is minimizing the communication cost, which is done by adding to this Hamiltonian a term which is just the sum of all the communication time. So this has two terms. It's heuristic because this is not the exact execution time. It's got two terms, one of which, if you minimize it, balances the CPU time, and one of which, if you minimize it, balances the communication time. And this has a very obvious physics analogy if you think of these as particles. The I and the J are these threads or grid points, what have you, which we think of as particles. The communication between these two the communication time goes to 0 when the particles are in the same processor, and it gets large when they're in processors far away. That's called an attractive force. They're trying to get in the same processor. The sum over k of tk squared is like a hardcore repulsive potential, because if you put all of them in the same processor, that term is a disaster. And so this is a very simple physics problem. We have particles running around in a space, the space of processors, and they have attractive forces and hardcore potentials, and we wish to find the equilibrium energy of this system, and that will be load balanced.
You're going to minimize the energy balance.
Yeah, and this sort of illustrates why this is not a difficult problem. We know that these physics problems do find their minimum energy, and
the question is not if it is difficult or easy to express. The question is now, once you have it formulated in this way, how fast can you solve it?
That's right, and you do various methods, and it works fine. Now, you will find there are 1,000 papers on this subject,
Okay.
and every single one of them succeeds. I made another statement on a previous talk that computer science problems divide into two. Those where every paper succeeds, and those where every paper fails. This field, every paper succeeds.
I mean, this is what Kirkpatrick did for IBM, laying out chips.
So this is just the Kirkpatrick algorithm expressed for this problem with
For this kind of problem first of all.
No, annealing is a physical process, right? Like when you cool iron,
I see.
you freeze in the various potentials. And
Optimization.
Kirkpatrick was a physicist like Jeffrey and I were, and he made this analogy to laying out circuits. And so
from that it becomes the optimization technique that everybody uses.
And you just minimize the energy by a Monte Carlo thing.
And you can do it by Monte Carlo, or you can do it by the so-called mean field approximation, which is an actual set of equations which does it much faster and not as well. You can choose which you want.
The Monte Carlo has some jiggling, so it has the advantage. It can get you out of local minima and get you to a lower one.
So you are claiming it can be solved efficiently and fast, and so it's a done.
And the diffusive methods, the matrix methods, the Monte Carlo methods, and you choose the one that has the appropriate ease of implementation and time complexity for you.
One of your books, Jeffrey.
Yes, chapter 11 of Parallel Computing Works.
Okay, done deal.
But the number of papers, there are packages you can download, and I would claim this for this class of problem, which are geometric. There must be some reasonably the mapping of geometrical problems onto geometrical computers always works well. That's my theorem. The geometry onto geometry is something which is there are very efficient heuristic algorithms which work very nicely.
Do people still write papers on this?
Not quite. Well, the 1,000 increases slowly, but that's a huge area. Yes.
I don't fully understand the formula. So the TK is defined by taking the computation of I that's going on processor K. What's the
so TK is the total execution time of the kth processor. It is the sum over all threads in that processor of the execution time of the threads.
What's the mapping between computation and processing? Oh, wait. So C is a data element, is it?
C is fixed. It's a compute time that you know. all you're varying here is the assignment of I to K, a particle or grid point or thread to processor. And you just run over all assignments, and these two terms force you to make the trade-off between communication time and equality of CPU time.
And why are we interested in the square of TK?
Because it makes it a feasible problem. Remember, these are heuristics, and the result of these 1,000 papers is you do not have to write the right answer down. You just have to write down something that has the right type of capability, and you use a reasonable approach to solving it, and you will get answers that are very, very good. That is because these are not... Mother Nature finds these optimizations easy to do. We're just trying to find Mother Nature's solutions, and these methods work. Some people do not look at communication time. This method does look at communication time. So these are all... You do not have to get these methods to work, you do not have to write down the... Remember, we can do sum of squares is much easier to do than minimizing, maximizing. You can do a minimax and things, and that's formally that's again, if you want to do the optimal answer, it's much harder. You can't use this analogy so easily. If you wish to get an answer that's very good, this will work.
Right. I represent the pragmatic face of parallel computing.
Oh yeah, and I'm a pragmatic person as well. I'm coming only from a different angle.
All right, so this silly slide here is about the dynamic problem. So we can think of this as particles interacting with what they're called springs here. These are the communication forces. And then if we do the dynamic problem, we have to put in the cost of moving these threads around. And that is basically an additional force, term in the energy, which basically attaches the particles to the processors they used to be at. So it's a similar physics problem. You just you just add a third term to the Hamiltonian, which is trying to attract the particles to the processor they're currently in, because there's a cost in moving them. And so you can now do the dynamic problem for this problem class. So Burton like this, so I will discuss the temperature of a physical system. Let's suppose we use simulated annealing, and we're doing this dynamically. Then it will take a certain amount of time to do this optimization, and if we spend too much time, it will be it will be a mistake, because we will spend more time optimizing the decomposition than we will gain from the better decomposition. So it turns out there's going to be a temperature. When you do simulating, you cool the system. So you're going to be able to cool it down to a certain temperature. If you cool it down more, you'll get a better decomposition, but it will cost you too much. So this says that you can think of this problem as a set of threads and processes in sort of thermodynamic equilibrium with the operating system, where the operating system is cooling them by moving them around, and they get into some balance, which balance reflects these various costs. And so that's the temperature of your system. So that's the definition of temperature for a general parallel system. And now we come to the difference between optimal and stable decompositions, which is the original thing I was discussing here. So this comes back to this domain decomposition versus a scattered decomposition. So I pointed out to Savas that these slides were prepared under oldest persuasion 15 years ago, which software package was driven out of existence by PowerPoint. And I am only able to reuse these slides because I happen to save the persuasion as JPEG or GIF images. Anyway, so this is persuasion. All right, so if we have, again, these entities and we want to do some nice geometrical decomposition, maybe something like this, the top thing here is the optimal domain decomposition. And it, say, has equal number of particles per processor. Here we have 4 processors, and we're trying to divide it into a nice geometrical fashion. Now here's a scatter decomposition, which is not nearly as good. Sorry, I couldn't spell in those. Probably persuasion didn't have a spell checker. So.
Don't worry, everybody knows what it means.
So, and then they say this scatter decomposition is not as good. And you saw what I did. I just took. There was actually a rule for doing a scatter decomposition. You want to look at the sort of inhomogeneity in the system, and you want to make certain that the natural inhomogeneity, which is this block here, that your processors all cover that grain size. So these scattered decompositions, you see, we're trying to keep some geometrical locality. We're not assigning particles in a scatter fashion. We're taking regions and assign them in a block fashion. And there is the region you wish to do is determined by this typical inhomogeneity in your system you're simulating. So there is actually an optimal scatter decomposition. If I chose if I made these blocks smaller, the communication costs will get higher. If I made the blocks bigger, I wouldn't be able to capture this inhomogeneity. So when we do our optimizations, we can optimize scattered and we can optimize these domain decompositions.
So all these seem to me that there are 2-dimension, and perhaps you can do 3-dimension.
You can do any of those dimensions. It's not. These ideas about block and scattered are nothing to do with the number of dimensions. I just draw in 2 dimensions. That's all. There's nothing to do.
Where I'm going with this is that they're dimension dependent, and with techniques like oct trees.
Yes.
Binary oct trees, in decomposing the problem, rather than decomposing the problem, rather than mapping the problem into.
So a typical oct tree that's what you, for instance, use to do the optimal decompositions for the fast multiple methods. They're all done with oct trees. So I don't think it matters whether we use oct trees. I don't think so. No. I'm just all I'm actually here trying to make is this point. There is a difference between the instantaneous optimal decomposition and the stable optimal decomposition. So this is shown here. So what happens, so this is some globular cluster or something, and it moves. So when the globular cluster moves, our optimal decomposition changes. And so we have to do dynamic load balancing. However, if the globular cluster changes the same size, the scattered decomposition is unchanged. So here's an energy diagram at the top. So you're plotting energy against some mythical x-axis, which just labels the decomposition. So this says that as the system moves, the energy curve for the domain decomposition changes. However, the energy for the scattered decomposition, remains a minimum. So it's stable. So this was your original question. That's why I did these slides. You asked about there are 2 approaches to the dynamic problem. You either track this and do the keep redoing the dynamic decomposition. That's actually how fast multiple is done. It tracks these changes and redoes the dynamic decomposition every time step. Because it turns out the computation is such that you can redo the decomposition every time step. However, other applications are certainly not true.
So I mean, in basketball, there's basically two defenses, man and zone, right?
Yes, this scattered is zone. That's right. So you're right. That's a good analogy. This is zone versus man-to-man.
Translate to an English one. I'm working on it.
Well, it must do some. Soccer must have some similar strategy. Next time you watch next time.
Soccer, they have a zone or man-to-man. Yeah, it's the same.
And there's no one is better than the other. They have different trade-offs. So that's right. So this says there's a difference between the instantaneous Hamiltonian and the time average Hamiltonian, and whereas the scattered decomposition is never the lowest energy solution for the instantaneous Hamiltonian, it can be the lowest energy solution for the time average Hamiltonian. That's what this top graph here says.
I wonder about the value of going deeper into the physics.
But actually, I don't think but this is a general comment on the whole field of complex systems. There are all these wonderful small.
Go too far into this. I understood the point about load balancing. I think that was what I was.
The phase transition at the bottom.
Oh, okay.
Fine. But the same, as I say, the same comment is true for small worlds and all of these beautiful things about network structure. You can go so far, and it's beautiful. The question is it significant thereafter? And I think the jury is still out on that. I stopped working on this 15 years ago because I didn't quite see what to do after having got this far. Because
good enough.
Yes,
it can be done.
Right, so now we're going to go back to what I was going to talk about, which is...
I find people still reinventing and republishing things which are well known.
This is true in any field where you think something is solved and there are these left behinds.
It's inevitable.
All right, so we'll start here. All right, so we'll start off with Amdahl's Law, then we'll do software systems. So still people are talking about Amdahl's Law, and I've already pointed out that I would view Amdahl's Law as a highly misleading law, because it says that there are sequential components in problems, which there aren't, in my opinion, at least not very often. But anyway, here's a standard picture, and it says that if the sequential component is x%, then the maximum speed up is 100 over x. However many parallel cores or CPUs you use. And that's a correct observation. So the only question is how big x is. So here's some trivial example. Supposing we were doing some sum from x over a sub I to form a variable x. And we have, as usual, the grain size little n, so the total problems of site big N, that's the number of points in the array. And then we did this in parallel. And we distribute the a sub i's on processors and things like that. And we could ask what the sequential component of this is. So there is a sequential component, x equals 0. There's also, as we discussed with MPI all reducing things, or at least on the distributed memory machine, some sort of logarithmic term when we calculate the total sum. So the Amdahl sequential component, something to do with order 1, and on some machines order the log of the number of processors. The parallel component is of order the grain size, because we're summing independently little n a's in each processor. So, as the problem size increases, the sequential component remains unchanged, and the parallel component gets more and more compute intense. And that, I believe, is a universal, at least in the applications I've seen, that feature is almost universal.
You're saying on these scientific applications, for large enough systems of a reasonable size, the sequential component. Amdahl's law is true, but the sequentially component is vanishingly small or extremely small.
It goes to yes, because it is almost impossible, you see, that the sequential components be a function of all the degrees of freedom, because that means we haven't parallelized it. So if you take an existing piece of software, it will certainly see Amdahl's law because it's not been parallelized. If you take a problem, I went through Intel's stack. None of those problems had these sequential components because all the large parts of the computation could be parallelized. So this is
So the parallel component here applies only to the memory access for A sub I. When you add up together, that summation actually is sequential, isn't it?
No, if I am doing this sum in parallel by dividing it between processors.
Or maybe little n, yeah?
So I have big N total system. So big N might be 10,000. Processors are 10, little n is 1,000. So we have 1,000 sums on one.
Of the AIs on each processor, so he's adding those on each processor. It's not a great example.
Oh, I see. Okay.
Not a great example.
Okay. So X will be XI. You're gonna I and then coming. Okay.
So you're doing a sum on each processor is what he's trying to do. But I think you could do a better.
If you look at the k-means.
That's the logarithm.
That's the logarithm. Okay, I understand. So it's supposed to be
We saw
XI.
this algorithm precisely when we did k-means last time. The k-means algorithm does these global sums. You do the partial sums. Actually, we did that for also the frequent item set matching. They also they had the same particular piece of arithmetic where you do partial sums independently on processors, and then you add them up. And the sequential part is some initialization and some adding, and almost by definition, the sequential part doesn't have any dependence on little n. How could it? Because it means that
there's no n in the sequential part.
Yeah, there's no little n or big N in the sequential part.
I think you should still be. I mean, obviously, for realistic systems, we need to be more cautious because there are large problems that, sort of by definition, were omitted from the Intel slide deck precisely because they don't parallelize well.
Be interested to know what they were.
What's that?
Interested to know what the problems they omitted were.
One general area that I would throw out would be graph algorithms. Some graph algorithms are parallelizable, some are more difficult. And that seems to be a fundamental theme in computer science that runs through a lot of what our software
is. Yes, of course, many graph algorithms can be replaced by other algorithms. That's because these NP-complete problems you can think of as graph algorithms, and we can replace them by heuristics which are parallelizable. So I am not so convinced that I have not seen a problem that somebody really wants to solve that we can't find an algorithm that can be parallelized.
It's when you have to build a very large, complex system that I become concerned. Yes, one specific problem we can parallelize, but if you look at our software systems, they can
Yeah, but that's because they're built as software. I would claim that's not because we had this long discussion. So I agree, Amdahl's law for software is undoubtedly correct.
We should be cautious.
Yes, but we can be cautious, but we should see what Amdahl's really saying. There is a typical problem which is not got large sequential components. A typical implementation certainly has large sequential components. So I do not believe Amdahl's law, which was stated at the beginning of parallel computing before DOE installed large computers. It was again stated then. It was proved out. I mean, this has not stopped DOE getting huge speed. That's because of effectively this argument here. DOE.
Yeah, but I think David's arguing the fact that you have a software system which has things which are parallelizable, but there are quite significant things which would be quite tricky.
Yes,
to
we need to really look at the whole.
Jeffrey was answering to the question. The implementation may not be parallelizable, but the problem itself, the solution could be. I want to make a comment. In my experience, it's just a surprising large number of problems can be eventually mapped to this parallel reduction, stream processing, and think of the MapReduce, this Google system. It's basically a parallel reduction. And they show not only it can be implemented in parallel, but also in a very distributed fashion.
In fact, some of the graph algorithms can be done, expressed as basically map these reductions, in fact, if you're sufficiently clever. But I still worry because I take a concrete example. I'm highly knowledgeable about compilers, and I look at all the many, many phases there, and I think about parallelizing the whole compiler so that it scales. And there's something where you basically can suck up as much computing time as you actually are willing to give to the system. It's not that it can't be done. I worry about it's the kind of thing, if you're working this area, somebody throws out, name your favorite problem area, could you actually parallelize this? And the answer is, it could be done, but it would be challenging. It would require rethinking fundamentally how to solve it.
Yeah, so that's why I said Amdahl's law says parallel computing is very hard, and it may be so hard that we can't parallelize it. That I agree. That's clearly true. However, that's a little different statement from the statement there's a fundamental sequential component, because it's often stated as though there's something fundamental there.
I mean, what you're saying is for scalable parallelism, Amdahl's law often doesn't apply.
And it seems to me that we need to, the only thing we can do is take real applications which people care about and say, how does it work? So all I can say is at least I tried to look at the Intel application stack and we didn't seem to be a problem there. Even for things like integer programming, which are pretty non-trivial and sort of graph, I mean, these are all tree algorithms or graph algorithms, whatever you want to call them. Those work fine because we can get parallelism. There is no Amdahl's law, as far as I know, for integer programming. So here's a little refinement of this about, say, multi-grid algorithms or hierarchical algorithms. So you can ask, what is the implication of Amdahl's law for a hierarchical algorithm where you start with a fine-grained problem and you basically keep decreasing the complexity of the problem by factors of 2 or something like that at each stage, and you eventually end up with a sequential problem. So, you said this. So multi-grid has a sequential component. What implication does that have on what's the implication for parallel computing? And the answer tries to be quantified here, that the implication for parallel computing is that there is an increase in communication cost, but there is no sequential problem. For the same reason, although this problem here is sequential, that the course's resolution, it takes time of order 1. This thing here takes time of order little n, where little n is the number of points in the processor at the fine resolution. So you will find that the parallel complexity scales like something to do with little n with no factors of the number of processors with this sequential component, which is in principle small for little n large enough. And you can it is true that as you reduce these meshes, the edge over area gets worse because the n gets smaller at each time. And if you do the arithmetic appropriately, you will find the communication overhead goes up 70% because of this multi-grid algorithm, because the average size is not little n, is smaller than little n. But it still goes like little n. So the analysis of hierarchical algorithms of this type, which is general divide and conquer algorithms, is there's no obvious reason that there is a problem. And that's all. That's the end. That's all I wanted to say there. So that's that. All right. So now we're going to do software. All right, so I would claim there are 3 broad classes of parallelism to be supported. One is coarse-grained functional parallelism, typified by workflow and mashups and things like that. We discussed that last time. This coarse-grained functional parallelism is particularly important. We mentioned MapReduce. That's a good example where there's some overall workflow, which is the data flow through the different steps, and then each step is actually data parallel. So in general, workflow is particularly important because it defines the so-called meta-problems, which are these composite problems built out of sub-problems, and those sub-problems which you're built out of would then have one of these three types of fundamental parallelisms. So workflow can be a workflow of workflow, it can also be a workflow of data parallel, and it can be a workflow of fine-grained functional parallelism. So the loosely synchronous data parallelism or data structure parallelism I discussed, that's this classic scientific algorithm. And the functional parallelism was illustrated by the discussion I did of computer chess and integer programming, where you have lots of threads with some natural application synchronization. And there are also the famous pleasingly parallel application, which depending on their grain size is either functional fine-grained or coarse-grained functional parallelism. So I believe these are the types of parallelism you need to try to support.
Embarrassingly.
That's pleasing.
That's the same as pleasing.
Definitely tried to change the name.
I didn't. It was somebody else tried to change it. Niren Lifney tried to change it. I didn't. But I'm happy.
Contemptuously referred to them as embarrassingly.
Yeah, I mean, for the first 10 years of parallel computing, we never considered embarrassingly parallel problems because we thought they were trivial. But
that kind of problem doesn't have to have any support, right? Just submit in parallel. Right?
I used to call it task parallelism. It's
task farms. It is the dominant grid application, is it not?
Absolutely, yes.
It is founded, though. So grid has managed to make embarrassingly parallel problems pretty difficult.
Thank you.
And the e-science program in the UK certainly had a major responsibility there. So.
Thanks a lot.
So anyway. But for this purpose, we can, because they'll often have some type of
Sam was just telling me in Newcastle that he set up a thing with embarrassingly parallel with Condor clusters, each of them running Windows, 2,000 of them around the university. Yes. People use it.
There's huge demand for it, right?
Yeah. It's just all the
so why should we work on all the hard problems when there's so many easy ones?
But that's why everybody switched to grid computing, was it not?
Yeah, exactly. So virtually all the training can be done by embarrassingly parallel.
There are many embarrassing parallels.
So I would say the advent of a lot of data has increased the number of embarrassingly parallel problems because the particle physics applications, which are enormously computationally intense, are all embarrassingly parallel. So it's clear that these problems are very, very important and they need some support.
So, I mean, your recommendation would be, and sort of my pragmatic thing, that for Mort programmers, you could provide support for these paradigms, and it would be relatively easy for them to see their problem fitted in this, and you could have libraries, and it would just work. Right. That's the sort of idea.
Yeah, I think there's a
so
slide.
That's no magic bullet, wonderful computer science. It's just rather pragmatic.
But also, could you knock them off one at a time and deal with the low-hanging fruit first?
Well,
yeah. So this is partly. Well, Burton will probably get reasonably, I don't really get angry, but I mean, these are all bundled together in the so-called HBCS languages. Yes. If you look at Fortress, X10, and Chapel, they have all three supported, which you can say is good. I mean, that's a feature of those languages. They support everything you want to do. The problem is you have to build a single language and a single compiler that supports everything. I would.
Like Ada.
My recommendation is, given the way the world moves so fast, that we should do one thing well, like you do the data parallelism for the .NET thing that David does, or CCR, you could say, does this, and DSS does that. I mean, it's better, I think, to focus on doing, at this stage, we should try to build good support for each of these things, and not worry too much about bundling them together.
Perhaps there is an equilibrium in the supported model.
That's right, yes.
Well, there's an interesting observation. I mean, this takes us into the HPCS takes us into a whole discussion. I won't disrupt your thing, but there's interesting conversations about how does a new language actually get adopted. And the usual universal way it gets adopted is it solves one problem really well for a set of users who really care about it. And that's why sort of Java exploded onto the scene. It was a good match for programming at the internet scale. It had new sort of libraries, and it was
although it was designed for embedded systems.
Yes, although it was designed for embedded systems, but so it does take us into an interesting discussion, which is these new languages. It's a very hard uphill battle to create an entirely new language.
So I'm afraid that we're rather pessimistic about that.
But David, do you think that's the only way a new language is going to be adopted? Certainly
we should save this discussion for later.
Well, I mean, there is another, Ada is another example which tried to do this, which is now hardly used.
Okay. There's the question of evolution versus revolution. Unfortunately, on the commercial side, evolution seems to have won out. But there is certainly room for revolution, but you need something that's just so compelling in terms of its...
So I have something concrete I want to throw out here, Jeffrey's comment. So in this paper we're finalizing for PODI this year, we have this classification, so two dimensions. Either the parallelism is explicit or implicit. And
that I come back to that thing later. That's the implementation.
I see the
This is a quality of the application.
Right,
whether we do it implicitly or explicitly I would view an implementation issue. That is what most of my rest of my talk's about.
I just want to say the other dimension is whether the synchronization is explicit or implicit. So that's
so these have very different synchronization models. This is a global synchronization point typically.
Workflow, basically explicit parallelism, explicit synchronization.
Yes.
Something like software transaction in memory that's explicit parallelism, but implicit synchronization. Well, okay.
Fine. So I think that's pretty reasonable. I don't think you'll find this is terribly different from the way you can always chop spaces up into different ways. This is the particular way I'm chopping this space up. So I discuss workflow. So I would view workflow as important for two reasons. It is the one area we have lots of good solutions. So this is not an area where we're struggling for a solution. The other two, I would say, we're somewhat struggling for solutions. Workflow, mashups, we're choosing between multiple good solutions. And different people may or may not like the current solutions, but I would say there are many examples of successful workflow, like the UK eScience did Taverna, which is highly successful. Other people think BPEL-based systems are very important, but these all work. And I think people find them reasonably productive. So I would say workflow is important for two. One, it works, and two, it is possibly the best way to think of packaging all these solutions, because it is the way you join things and compose things together. So if you've packaged all the other things as libraries, some workflow environment, or possibly not at the internet scale, but internally to the chip of how you do these coarse-grained parallelism is pretty important. So workflow characterizes the overarching paradigm, and the paradigm, because it doesn't have these stringent constraints, is got the best solutions.
When I think about workflow, I don't think about parallelism. For me, a workflow is something that reflects much more an application-driven way to think about doing something. For example,
let's call them mashups or orchestrations.
No, I think about workflows. Think about business workflows.
Yes,
they are ways to organize complex tasks into units of work, atomic units of work from a business point of view. And how do you later on execute them? This is a completely different question.
But if you have a continuous stream, I mean, I agree that the workflow, which is just like an expense report, there's one item and it just goes through a series of things. But if you have a stream data coming in and you want to do all these different tasks, then it is parallel.
So when the grid...
You can do it parallel, but it is not inherent. It gives you a way to do it in parallel, possibly. And by the way, taking workflows, sometimes it's very difficult to find parallelism because people confuse the dependency that is time-wise versus the dependency that is caused by intrinsic functional dependencies.
So even in the business world, though, you do have branches in your workflow.
Branches doesn't mean automatically parallel.
Well, a branch will probably mean that two activities or two sequences can happen in parallel or concurrently.
That's something different.
Well, I complained. I complained when the grid community used the term workflow to describe this type of computing, because of the reason you said. It confuses it with business workflow.
Don't let us get hung up on it. But I'm much more in the workflow way, much more driven by the applications rather than thinking about the grid there.
But this particular type of orchestration, which is coarse-grained, loosely synchronized. Coarse-grained synchronization has been given the term workflow in the community. I happened to complain when it was done because I said this is going to be very confusing, but that term has still used. It is, I say, being replaced by mashups in the real world. Anyway, so that's that. So this is really Tony's point. So this is the lack of programming paradigm model. I mean, maybe we don't need a programming paradigm because we'll just use Caltech graduate students to write all the libraries and Microsoft research interns. That's it. And then we will capture all the Intel stack and all the graph stack as the optimal algorithms, and we will just present it to the real world in terms of much simpler interfaces where they can manipulate these libraries. So that is one approach to parallelism.
This has nothing to do with your DoD work.
No, this is just remember there was back in '92 we had the Pasadena meeting and we had things called templates which are closely related to this. So this model that you captured certain parallel computing styles in various ways and reused it is consistent with this. And of course this is rough. A lot of work is done in this fashion. People reuse libraries like Petsy and things like that, and it is not quite so obvious how much parallel computing has to be done by the real world. If you can capture enough, if you captured all that Intel stack as parallel libraries, it's not so obvious that you couldn't compose those things to get real applications with a much simpler problem. That's a much simpler problem to solve.
Less than optimal overheads because you composed them, but nonetheless it would be.
But then each would run. Again, this is a question of where the critical overhead is. Then each would, if the parallel execution is the dominant compute time, and that's done very efficiently because we use the Marine Corps to code it, then maybe that would work.
So the risk in this, of course, is you end up with a bunch of over-specialized libraries. And so we go to look at it and take it off the shelf for some application, but it doesn't quite fit. And we can't quite figure out how to customize it. And the only way we can customize, it's a very reasonable model that you're proposing, but the risk is that the question is how many variants on these things do we want?
Yeah, when I was doing scientific things, I never found a library did exactly what I wanted.
Yeah,
but we're talking about morts here. Right?
Yes. And and that's exactly what I'm worried about is that.
So whether you could get libraries of sufficient generality.
Yes. But there's the opposite danger, that you will look at the library and say, it's not quite right, I can do better. 2 years later, you finish doing better. And the library has already improved because the Marine Corps was still working on it.
There's the intermediate approach, which people look at the library and say, it doesn't quite do what I knew. Could you give me the source code and I'll modify it myself?
Well, that actually
a year later, they throw up their hands having botched the concurrency and, not really. They ship it out and say it works right, and then somebody else, the calls start pouring in about it. It doesn't work on my computer.
Well, I'm just noting that this is, because that again comes back to what problem we have to solve. It is possible we don't. Right. So. All right. So this is sort of implicit versus explicit parallelism. We can either program the parallelism explicitly, when we break it up into parts and we write the code for each part, Or we can write the program, which is the complete application, and let either the compiler or the runtime decompose it. So it's program parallel or...
That's what we discussed. The last thing will not work. I mean, this will not work. This is, from my point of view, a dead end.
Well, I don't believe our friend at the back would agree. You mean this doesn't work?
Yeah. I think...
Well, you would not get many people... I mean, I'm just giving a talk. I would say that that certainly the compiler community as represented at the back would not agree with that statement.
Is that an observation of prediction?
Well, no. We discussed on the first day, we said it is very difficult to rediscover many of the semantic issues that get lost in the programming, rediscovering them, and then using those to do the parallelization. I think at least I agreed on your statement that we need other abstractions that still cover the necessary information that is needed to refine a general statement, and during the refinement process doing the parallelization.
But that's, of course, the HPC, let's come back to HPCS as a neutral field. They are redoing that whole language so that they can express it in a different way for which the program where we do not lose the information.
So gentlemen was looking at the parallelizing integer code, for example. But one promising direction, I think, is for the automatic tool to sort of help the programmer to figure out where parallelism failed, and then to help the programmer to sort of easier way to specify or
You see, I'm coming from the database field. It has been very successful to use SQL, but I think for data processing, SQL is not the end of the world. I'm self-critical enough, so I think we need different paradigms, and in that direction, I'm much more a supporter of functional programming, which might not be the golden, the silver bullet to solve all the problems, but I think this paradigm goes in the right direction, where you, in a very abstract sense, define certain aspects of your programming without giving the nitty-gritty details. And then you, as a compiler person, you have the freedom to do whatever you like under the cover to satisfy my needs for efficiency, for whatever.
Yes. But there is a reason function of languages are not really cannot be general purpose because you don't reuse data. I think that's a serious flaw that cannot be automatically healed.
They don't reuse
and the
data.
moment the programmer starts to reuse data, and then we get into all these
have a notion of state.
They have no notion of
Yeah,
state.
the
No, I
problem of
understand.
state is a crucial problem there. I agree.
Right.
That problem existed back in 1980 when I started working in this field, and I was told that functional programming would solve this problem.
Me too, I was told the
Same.
And we are still...
The world isn't as black and white. I mean, if you look at some of the languages, they try to rectify it, not in a very nice way. And again, data is my field, so I can see the problem.
So, but this is, I would put that as this type of paradigm where we're trying to capture the complete application in, say, a functional or declarative fashion. That's fine. So that's part of this model.
There's clearly a tension. When you say one writes the program to describe the whole application, that's sort of the key phrase. You could have a programming language that did let you do sort of NPI programming at maybe a higher or nicer level, but it's basically NPI programming processes.
It goes down to
processing
NPI,
yeah.
but could be...
Well, that's
Yeah,
called...
so I'm just saying
I
the whole
agree.
issue of how you describe the program and then what you rely on the compiler and the runtime system to do, that interplay is the crucial issue. And I think that in general there's a limit to what the compiler and the runtime system can do given a certain description of the program.
Unless
the
it
problem-
can recognize these patterns.
To pull this into the reality is that the way people program right now, they program at such a low level using languages like C and things like that.
We are polluted by our...
Well, they program at such a low level that there's almost no freedom left.
Yes.
I think we're getting stuck in details. I mean,
Yes.
let me think about a simple detail with something like we're too worried about what tools we happen to have in our tool bench. And actually, I think a bigger problem is what are we teaching the next generation? So if I think about when I went to school, people in my generation actually did get PhDs in computer science, but probably the next generation before us didn't, right? And the things that we were taught to think about were sort of very serialized abstractions.
And procedurally oriented.
Oh, Well, no, I mean, that was a big debate. It was very functional, actually, where I was. But that was a hot debate, okay? Now, it's not maybe relevant or whatever, but what I would be concerned about is what is the abstractions, what is the reality that the next generation is facing? Now, I could imagine they're actually in an obviously embarrassing parallel world where the web is sort of everything in your face, and you kind of assume that you have no synchronization really or anything, and it's just a different world. We're not worried about procedural declarative, we're worried about different issues. But I would think what's really at the core of this is people think about what they know how to think about, and what are we training the next generation to think about?
But we're not training them to do parallel computing, because as far as I know,
there
are no classes left on that. When I went to Syracuse University in when I taught a class in 92, I think I had 80 students in my parallel computing class. In 2000, when I left Syracuse, I had 3.
Yeah, I don't think it's quite as bad as that, but I agree.
Well, there are not many.
Now we're talking about Moore's law is going to run out of steam, right?
No, I feel it's
Yeah, so we're re-looking at parallel computing, and I do think we need to re-look at the education, because we're not educating many students to be able to think about this.
But maybe not at this level of detail. The question would be, when you specify an algorithm, like a graph problem or something, do you specify, how do you do that? How is that done now?
So I'm not as pessimistic as I was about functional programming, actually, and I think a declarative thing could have a role to play in this one. So
let me give you an answer to that. Will you teach today people how they have to access the data on disk? No. This is a solved problem from my point of view, because you have database technology, you have proven technology, and it actually gives you the way to access data declaratively. I think this has been
well, that's the Marine Corps.
I agree with you.
So I think we need more of these kind of successes in other areas. I don't know if...
Well, isn't that roughly what I'm saying here? That we try to capture as much as possible as libraries?
Well, library is already for me it already suggests a mechanism which I agree to.
Fine.
I'm more thinking about how do we teach, say, an algorithms course?
Yes.
Would an algorithms course sort of assume, we had machine abstractions, which were inherently kind of procedural machines. How do they do it today?
That's an open. What abstraction you use for the machine is an open point of debate. What notation you would use?
No. In an algorithms course, if you open up the
if you open them up now,
what used to really get me was the PRAM model.
Yes, that's what I'm getting at.
Multiple processors, instantaneous access to memory, no memory hierarchy, no network. It was ridiculous.
Right, and now the question is, how is algorithms taught today?
Well, people like Michael Quinn down in Oregon actually are sensible and has a book on this subject. We could go look.
Can you give the essence? I mean, not only saying there's a book out there. I mean, what is it? I think the gentleman is right.
No, but you need to worry about these trade-offs, the latency and
should I tell you? I don't want to worry about it. There are experts around. They should worry about it, and I want to get a mechanism that I say, these are my requirements, you solve it for me.
Okay, but a lot of people are taking algorithms courses, right?
But even for algorithms, what is algorithms? Algorithms is an abstraction, and when you put that to work...
No, it's the name of a course that you have to take to get a degree.
Well, if you look at graph algorithms, I look at them not in the context of a particular architecture. I look at them in an abstract way. But if I want to throw it on an architecture, then I want to have abstractions.
I'm just an undergraduate. I just want to graduate.
No, but I wanted to do a course on performance programming. When you did an algorithm, and you did it one particular way, you had some idea the performance penalty of doing it that way, and we've never done that and never succeeded in doing it. That's the sort of implication that you want. You want to know that this can be done. If you do it this way, you get this percentage trade-off. Well, maybe that's the compiler. People can do something on that.
To go back to the SQL thing, by the way, I mean, there's libraries that don't, it's a much richer thing than it used to be, say, 20 years ago.
Very, very 10 minutes
Jeffrey, finish him up.
Sorry
That's fine. I believe this will have more impact on Microsoft than anything I have, and you can always look at my slides on the web, can you not?
Yes.
So here's some examples of these various approaches with program parallel approaches and component parallel approaches, and here's an example of one where you could either say this is good or bad. You try to make writing NP a little easier by using global array indices to be able to generate automatically the MPI calls. Here are various threading models. We've already discussed workflow discrete event simulations of this type, and of course MPI. And at the top are the many program parallel approaches, where I would put the Microsoft.NET data parallel approach up at that level.
Only a little side remark, sorry to interrupt you again. The MapReduce is a good example where functional ideas have been put into action, because MapReduce is nothing else than taking a functional paradigm and put it into action in a very specific place. And I think we need more of these kind of things.
Yes, so as part of my homework, I added MapReduce to these slides. I discussed it in detail last time. It seems to me a very reasonable model. What it does can also be done in many other ways with this notorious workflow technology, but it's all of this, but it's of this type. But MapReduce has done something rather nice. It's taken various useful document-related parallel algorithms, it's captured them, placed them on Google clusters, and it's given, as you say, a very nice user interface to allow you to express the pipelining of data through these algorithms. So I would say that's a wonderful example of what I call the Marine Corps model. The Marine Corps built the parallel document processing algorithms, and they produced a nifty interface that almost anybody could use. That I would view as a clear example of how you might approach parallelism. That, I think, is a good example of that.
But again, the MapReduce is an example where you worry about the parallelism, I worry about my application, and we can somehow go about it separately, and through the right interfaces we can glue it together.
Yes, and so I agree entirely. If we can show that all applications can be done with a possibly richer language than the MapReduce, it would be richer language, can be done in that fashion. That was my original proposal, that we capture all parallel algorithms, probably programming it in this manner. Because these are the way the Marine Corps can program. They can program with this stuff. And we just capture them all.
And you have a language
and then we can have a language which can be declarative, or can be whatever language you like. It can really be many languages. And we just capture them all, and you compose your application in that model. I would say that is the most optimistic approach to parallel computing, because that we could deliver.
That's what you're going to do with my TCI funding, is that right?
Well, we can discuss how that do that.
Let's take that
If that's what you think is inciting, that is actually not so difficult to do. That is not so difficult to do.
The discussion of the last slide.
How many slides does, I really want to see the answer.
Sorry, yeah.
What's the difference between program parallel and component parallel? You spelled that out.
Well, program parallel,
what distinction do you draw between C++ features and OpenMPA notation?
well, I pointed out at an earlier slide I skipped over so we could finish by 12. that when you started looking at threads inside existing languages, the difference between program parallel and component parallel got a little vague. But at least here with futures and active objects, you are programming the component. You happen to be using C++ to orchestrate their interactions. So that's the program parallel part. So it's actually a mix of program and component parallel. But to make that work, you have to explicitly have the component written, which is the thread, as you do with CCR. You had those. I would say those are the task of the user. The question is whether the user has to write the code for the individual parallel components or not. And I would claim in these approaches here, the user is responsible for writing those component codes. And one of the advantages of the C# based thing here or the C++ thing here is that you have a natural existing language to do the orchestration in, which many people are familiar with. So those are reasonably interesting approaches which could be quite successful. And we are not going to fit, the
most important slides.
Well, they've certainly got the most debate. So, but you see, if I'd started with this, we would have never done load balancing. So I did load balancing first. Otherwise, we would never have got to those slides. So, so here is some classic type program parallel operations in, say, high-performance Fortran, where you just write everything as arrays or as library routines, operating on arrays, matrix multiplication, shifts, and things like that. And those are, I mean, that is classic what I call data structure parallelism here, to distinguish it from data parallelism as a structure of an application.
This is more like a MATLAB.
Yes, except this is designed, this was explicitly designed so a compiler could take those instructions and parallelize it.
But does it have to specify how many nodes you have?
There were constructs you could do to specify that and how you decomposed it. Jeffrey was one of the inventors.
Oh, the user doesn't have to know much about it, so that's the kind of thing.
Well, it never succeeded quite.
Well, that's why it says here, HPF had lots of problems. My group produced the first compiler. It was licensed by the Portland group. Well, I don't know whether, I doubt if they still make it. The problems it had was probably the unexpected problem was unpredictable performance. I would think that is a really serious problem which we did not predict. Because of the automatic nature of the parallelism, we could not, so when it didn't run very well, it was very difficult to know what to do. Whereas that contrast with the component parallel approaches, where because you programmed it, it was a lot easier to do performance debugging.
Same as a vector, sometimes you got poor performance on a vector machine, right? So it's a similar thing.
But we did not predict that as a major difficulty. And this we did predict as a major difficulty, that we weren't able to express all problems with it, because HBF was an early attempt to do data structure parallelism and didn't have everything in it.
So just to help me ground here, Cray and stuff had various Fortran extensions and then Alliance and things like that. Is this after that, or is this?
That is after that.
This is like connection machine Fortran.
This is exactly the same.
But this predates what, Cray and Alliance and stuff like that?
No, it was after that. Those were aimed more at what I would call local although it's slightly related, they were aimed at vector instructions, which if you go back to some original slide, says we have outer loops and inner loops. So the Cray things were more aimed at the inner loops, and this is aimed at the outer loop parallelism. The domain decomposition. The Earth simulator had a good HPF compiler, and all of this is effectively replaced by the HPCS languages. All the people used to work in that type of field now work on the HPCS languages, for which there are 3, X10, Chapel, and Fortress, and they're still being worked on. They hope to address this problem. What they don't obviously address is unpredictable performance and whether they actually can parallelize correctly this thing. I think it's not obvious. They obviously are better than much better than HPF, which they ought to be. They've got 12 years of experience built into them, so that has to have major impact.
So I have a question for you. If you look at something like MPI, when somebody writes that, they clearly have a way of thinking about how they're mapping their data onto the computer. But they're just writing a program down, so they're not actually having to write down the formal mathematical mapping necessarily of how the data is being mapped. With these languages, my impression is that you actually are trying to write down some mathematical notation or some notation of how you're actually doing the data mapping. So it seems analogous to a programmer, when they write a program, has a notion of correctness, but we don't usually force them to write the notion of correctness. And so one question here is it that we're trying to force the programmer to write down their data mapping that is a fundamental?
Well, I must admit I have not looked in detail. These languages allow you to specify, as did HPF. HPF allowed you to specify decompositions.
You scatter, or you can evolve various ones.
And
the question is, why is decomposition for MPI feasible and decomposition for these languages terribly unpredictable?
To work at the MPI decomposition too.
Yeah, I mean, it's because the Marine Corps was able to do it. That's all. The Marine Corps can look at the application and know exactly what to do. To get a compiler to to capture the expertise of the Marine Corps and take some abstract expression and find the correct optimal way of doing it, which is highly non-trivial. Usually there are all sorts of choices which are relatively straightforward for users to understand, and to put all that expertise into a single compiler is incredibly difficult. Well, it's not, it may or may not be, I don't think there's anything very deep. Yes. Well, I've already said all this stuff. HBS language have one important feature. They do everything, but maybe that's their weakness. It's a disruptive technology, but maybe it will never be allowed to disrupt us.
So for this language, how much do users have to specify about the details?
Nobody, as far as I know, has written a real problem in these languages yet.
Callahan must know. He must have been involved in the chapel design.
Their implementations, from what I understand from talking with people building this, they sound like they're years away from.
That's right. They're many years from
Can I
usability.
also we let Jeffrey finish, and then we'll continue the discussion.
Okay.
Well, I'm not going to finish. Let's see if there's anything.
Well,
Let's skip this stuff.
Final slide, because it's past 12 already.
NPI. All right, so we might as well at least formally do NPI. It's hard work. It always works and has a clear performance model. That's its positives. It is also universally, as I keep saying, it is universally used. I asked David Bernhardt at Oak Ridge, what do they use on their problems? All use NPI. They do not use OpenMP. It's just universal.
For the weapons labs, they all use NPI for scaling across
We've
labs.
discussed the execution model. Here's the features. And this is Tony's problem. Here's just a list of all the functions in NPI. The previous slide had the 6 you actually need. Here are the 300 in, this is NPI 2, 300. Here's an important slide. So this is performance. So here you have latency. Look at the left. The latencies are measured in microseconds. And that's the critical feature of NPI. That the implementations are very high performance. They use network cards optimally. They're all optimized to get incredibly good performance.
There is one key lesson, though, from the Cosmic Cube days, that you did a very low latency in order to get microsecond latencies. Intel produced a machine, the Intel personal supercomputer, where they put full Unix on each node, and their latencies went from microseconds to milliseconds, and the performance was just diabolical.
And they almost destroyed parallel computing.
No, and that's, you just have to think about that in the context of Windows. Right?
Yeah, that's a good lesson. Here's another NPI performance, again on a multi-core chip from Ohio State. That's also microseconds. People like it because here's various performance things, but it gives universally, NPI always gives good performance. The other approaches sometimes gives good performance. And I just wanted to mention, I'll finish here. These are interesting languages, it's interesting actually they're not more successful, where these are typified by CoArray Fortran, Universal Parallel C, and Titanium from Berkeley, where you write the program for each component, but the system, the system generates automatically the NPI calls. So these are a class of languages which some people say they're wonderful. Their use is again almost negligible. And this idea is again in the HPCS languages. The idea is to try to make the generation of the messaging more automatic, but still allow the user to define the components. So that's sort of the idea, that we try to make the actual generation of the, if you like, the formal NPI calls and collecting the data together and packaging it and sending it a little easier to do. And you do that by having global indices, but from the component. So you still write components, but you use global indices. And we will stop there. And all of these slides, including some of the many details we didn't go through here of the software, are sitting on the web. And I should say, I mean, as David, I think the Microsoft.NET Data Parallel System is a good example of things that will work according to these principles we described.
So, I think it has been 4 very interesting days. Let's all thank Jeffrey for his